So we are all excited to get started learning how to produce sustainable hydrogen with the help of solar power. And so I introduced the first lecture, Introduction to Solar Hydrogen Generation. There will be three speakers. First, Professor Roberto Gomez, who is our project coordinator of the photo-H2 project. Then the second speaker will be Dr. Antonino Arrico from Siena Research Institute in Italy. Antonino is the group leader of the research team at Siena working on photo-electrolysis, and the University of Alicante and Siena are the two key research institutes developing the photo-electrolysis technology in photo-H2. The third speaker will be Roberto Macus from Hygear, and Hygear is the company providing developing and providing hydrogen storage equipment. So all of the auxiliary equipments that are collecting, drying, and storing hydrogen are provided by Hygear in our project. And together with the photo-electrolysis panels and the Hygear equipment, we have an integrated system that will be introduced. So this introduction will be an introduction of the complete concept and complete system for hydrogen generation and storage. So without further ado, I will give the screen sharing to Professor Roberto Gomez to start the presentation of our webinar.
Thank you, Andras. Let's see if this works properly.
Yes, your sound is working, and I think
yes,
your screen is just coming up.
See my screen.
Yes, I see your screen now.
Okay. So if you can see my screen, I will start with the presentation. Okay. So as Andras said, yes, we are pleased that you joined us today in order to get information on the activities that we have been developing within our project, photo-H2. And not only the theoretical and more fundamental aspects will be covered, but we will also advance some of the solutions that we have applied within our project. So it will be a mix of basic concepts plus solutions implemented during our project. So the first lecture is on the introduction to solar hydrogen generation. But I will start with a very brief introduction of the project consortium and the main objectives of our project. So, okay. This is the logo of our project, photo-H2. Photo-H2 is a project in which there are 5 partners. One partner is the University of Alicante. The University of Alicante is coordinating actually this activity, this project. We also have Hygear in the Netherlands, a company, an enterprise in the hydrogen business actually. Hygear is actually a hydrogen distributor and supplier. We have ATS, which is an Italian company, an Italian enterprise dedicated to advanced fabrication processes. We have Broadbit, which is a company working on the different energy technologies, including solar water splitting. And we also have, of course, CNR. CNR is the National Research Council in Italy. Actually, the institute participating in this project is based in Sicily. So these are actually the main breakthroughs targeted in our project. So the concept of photo-H2 is based on the development of a highly efficient tandem photoelectrolysis cell for solar hydrogen production, based on durable and cost-effective advanced materials and interfaces. And then I want to emphasize this. So the project aims to develop a tandem photoelectrolysis cell, but based always on durable and particularly cost-effective advanced materials. This is, I think, an aspect that should be kept in mind, because of course, if we work with cost-effective materials, we have to pay a price sometimes in terms of efficiency or durability. But I think that, or we think actually, that the correct direction in order to have a technology that can be mass deployed later on is to work with durable and cost-effective materials. And then, if I try to be a bit more specific on the materials that are, being used within photo-H2, I would say that the electrodes are based on earth-abundant transition metal oxides. This is our aim from the very beginning of the project, to work with already known photoelectrodes based on transition metal oxides, and also the initial idea, and we have worked hard in this direction, to find new oxides that could be good electrodes, either as photoanodes or as photocathodes. Another aspect that we wanted to develop or that we want to highlight actually in our technology is that the idea is to have a simple flow cell design. A simple flow cell design that should be easily scalable. This is an aspect that sometimes is not regarded in detail in the case of photoelectrolysis or photoelectrochemical devices. So from the very beginning, all of our efforts have been directed to have a technology that is scalable. So our demonstrations should put the basis for having larger pilot plants based on this technology. A very important aspect is that the idea was from the very beginning to work with a system fed with pure water. That's very important, and it makes a difference with the typical photoelectrolysis systems, in which it's a bit more complex, the input of water in the system. Of course, water is being consumed during the process, but you'll see that the solution provided by photo-H2 simplifies very much this aspect. And of course, the idea is that the output of the device was pure hydrogen, pure in the sense of dry hydrogen, as dry as possible. We are conscious that, of course, normally this will not be achieved simply by the photoelectrochemical device, and that ancillary equipment will be needed in order to have a really dry hydrogen. But these are the main breakthroughs that we wanted to achieve from the very beginning of our project. And this is the configuration that we devised at the beginning, and we have been developing during the last 4 years, almost 4 years now. So as you see, we have a tandem configuration with 2 photoelectrodes. And the 2 photoelectrodes in tandem configuration. We could have chosen a parallel configuration, but it is more efficient from the energy point of view to work with a tandem configuration. So then the idea is simple in principle. It is already known from the very beginning of the photoelectrochemical developments in the 70s, I would say, the idea of having a tandem device. As you see, it's simple, but has some novelties with respect to the typical tandem devices we can see we can find in the literature. We have, on the one hand, one of the photoelectrodes here, which is supported on a transparent FTO substrate. We have another electrode here. In our case, this electrode is the photoanode, and they have the photocathode supported on a porous hydrophobic backing. This is a major novelty and a major breakthrough of the technology being developed within Photo H2, I would say. Because the idea, of course, is that the hydrogen produced at the photocathode surface is retired or is extracted through the back of the electrode. If this carbon-acid support is hydrophobic, in addition, we achieve a high degree of dryness in the hydrogen being extracted from the device. It is also very important in our concept that the electrolyte, which is sandwiched between both photoelectrodes, it's a transparent ion exchange polymer membrane. In our case, an ion exchange polymer membrane. So these are the aspects that constitute, in our opinion, novelties, I would say even breakthroughs in the photoelectrochemical technology for water splitting. One of the reasons why we thought that this was a very good idea at the beginning of the project, when we prepared the proposal, is that this configuration is rather flat and easily scalable. As I said, this was one of the targets in the project, to have a technology at a rather small scale at this point, but that could be eventually scaled up. So it's important that the configuration is rather flat. Yeah, here in more general terms, I've presented, or I just want to cover very quickly the different conversion technologies for solar hydrogen production. As you see, there are here in this picture 6 main technologies being covered, actually 7 being covered. I would say this is the most mature one, is the combination of PV and electrolysis. Because both technologies being coupled are at a very high TRL. So this is mature and commercial. We have the photoelectrochemical water splitting. So our project is devoted to developing this conversion technology. We also have the photocatalytic technology, which is to some extent and in many respects directly related to the photoelectrochemical technology, with some advantages and some drawbacks, in particular because in this case it is much more difficult to separate the product of electrolysis, while in a photoelectrochemical device this is much easier. We have the thermochemical approach to have solar hydrogen. In this case, we are not using photons in a direct way, or I would say we do not convert photons into electrical carriers and then we produce hydrogen. In this case, directly thermal energy is employed to produce fuels, for example, hydrogen. We have also this photobiological approaches which are being developed right now. Of course, this depends very much on the stability of the cultures. For the microorganisms, is something that is at a relatively low TRL. We have hybrid systems in which we combine both a chemical and a photobiological system. We have this photoelectrochemical device in a way which not only is able to drive the generation of hydrogen, but also the oxidation of another product, of an organic product, instead of oxidizing water. This is in a way a photoreforming process. And then, as I said, our project focuses very much on the development of a photoelectrochemical device for water splitting. So this picture, by the way, is taken from the document Innovation Challenge 3. I like it very much because it summarizes in a pictorial way the technologies that are being developed for solar hydrogen production. Here we have the a SWOT analysis that I performed. It's my personal view on this, of course, take into account that it's arguable and debatable what I've written down here, but it's just a SWOT analysis on the photoelectrochemical solar hydrogen production, the way I see it at present. So there are, of course, as always, strengths, opportunities, weaknesses, and threats. Regarding the strengths, I would say that this technology allows for the direct use of solar energy to produce hydrogen. So it's, as I mentioned here, a monolithic, simple device, the one that is going to produce the hydrogen and oxygen. And that's important, I think. There's no requirements of coupling with another device. It will be different for the PV plus electrolysis approach. It provides for the direct storage of solar energy as chemical energy, of course. In principle, it could be more cost effective than other technologies, but of course, this will depend on attaining certain values for the relevant KPIs. These are, I think this is also critical, or a very important strength of this technology. You can have standalone devices, and this allows for the distributed generation of hydrogen. So it is something that we should consider if we want to be independent from the grid for the production of fuels. And then also it's important that water flow in flow systems, it's not only providing the reagent for the process, but it's also allowing for the thermal management of the module or device. These are the strengths, in my opinion. There are opportunities linked to these strengths. Of course, there's a potential breakthrough by developing the first commercial module for water photoelectrolysis. I think that these developments are favoring technological innovation in the EU industry. It is true that we have support from European and national research and innovation entities. There are funds available at present for developing further this technology. And of course, as I mentioned before, through this photo reforming, it is possible to co-produce a value-added chemical if we change the oxidation process from water oxidation or oxygen generation to the oxidation of an organic product, producing, of course, an added value a chemical.
Roberto, can you please try in 3 minutes to hand over to Antonino?
Yeah, sure. And then the weaknesses are of course, and this will be obvious later on. The durability of materials and devices is poor at present, so this needs to be improved. This is going to be practical. Solar to hydrogen efficiency is still low for cost-effective materials. This needs to be improved also. System capital cost is high because of the need of larger active areas than in the PV plus C configuration, in the PV electrochemical configuration. Balance of system cost is also high because of low productivity. And of course, there's a lack of clear business case and also a lack of codes and standards. These are, of course, weaknesses. And linked to all these weaknesses, there are threats, uncertainties on the viability of hydrogen cost, because we have this target. This target is a very, very difficult one. And of course, we also have uncertainties on the potential commercialization of these photo-electrolyzers after I would say over 50 years of research and development without a clear success. And then, of course, industry feels too risky to invest in this technology. And there's very strong competition, as I said, with the PV plus electrolyzers technology. So this is just a guess of the technology reach for the photoelectrochemical solar hydrogen production. We are here. The hydrogen production per square meter and year is very low in terms of energy. Taking into account the solar irradiation in Alicante, for example, amounts to 1,800 actually kilowatt hour square meter year. And today we can say that the hydrogen production it scales up to 30. So this needs to be improved. I think that it's reasonable to think that in 10 years or so, we could reach 100 kilowatt hour square meter year, and also durability could be increased in 10 years from less than 1 year now to at least 1 year. Of course, if this is going to be a technology in 30 years, say, we still don't know. It will depend very much on the success that we have in developing the research and viability and testing of this technology in the next 10 years. Well, I would like just to benchmark results in the literature. Well, this is for sure the best result obtained until now for a system based on oxides. As you see, the solar to hydrogen efficiency is low, the stability is not that high, and also we're employing here, they were employing costly materials such as ruthenium, gold. So as you see, the best benchmark results in the literature on water photoelectrolysis are still far from being practical. Benchmark technologies. Well, let's think about solar hydrogen production through the PV plus electrolyzer combination. STH efficiency up to 15% have been achieved. So we need to be close to this value in order to make this water photoelectrolysis viable from a technical and commercial point of view. And the cost currently for hydrogen production is of less than €2 per kilogram. This means that we need to also to decrease very much the cost of all the materials, production techniques, in order to reach this goal. And that's all. I will hand over to Antonino. Antonino, please, you can continue with the photoelectrolysis or photovoltaic plus electrolysis technology, a brief description of it.
Yeah. Thank you, Roberto, for your introduction. Can you see my screen?
Yes, we see your screen.
Okay, now it's in full presentation mode. As already, I would like to thank Andras for the organization of this webinar on photo-H2, on the photo-H2 project. We are belonging to the Italian National Council of Research. Our institute is the Institute of Advanced Energy Technologies participating to this project. So regarding the hydrogen production, the green hydrogen production from renewable power sources, as already mentioned by Roberto, the option of photo-electrolysis, photoreforming, and other relevant processes are for the long term. Actually, the state of the art for green hydrogen production is based on using renewable energy as energy feed for electrolysis systems that could be alkaline or PEM electrolysis. And the produced hydrogen can be stored or injected into the gas grid, can be used for the industry, for the chemical industry, the ammonia and methanol synthesis, but also for providing high-grade heat for industrial processes. And through fuel cells, hydrogen can be converted again into electricity or providing heat for combined heat and power applications. So this slide is essentially summarizing the hydrogen economy, and the hydrogen can really be an important energy vector to decarbonize the energy system. The future energy system. So I would like to say a few words about the European policy in this context. As you know, the target of the European Union is to achieve carbon neutrality at 2050. And the hydrogen strategy was released last year in July 2020, according to a communication from the European Commission to the European Parliament. And the hydrogen strategy was detailed in this communication. So the targets are 6 gigawatt electrolysis plants installation by 2024 and 40 gigawatt installation in Europe by 2030, worth up to 10 million tons per year of renewable hydrogen production in the EU. It is also important to consider that the European Commission is also sustaining the installation of 40 gigawatt also outside Europe using European technology. So this is the European strategy, but of course all, several countries have addressed according to national strategies the green hydrogen production. And you can clearly see here which are the targets for the next period. So hydrogen is really becoming important to decarbonize the energy system. And of course, there are several approaches, and we think that there is no unique solution for that. So depending on the conditions, we can use different approaches. At the moment, the state of the art is based on 2 low temperature electrolysis technologies, alkaline electrolysis and PEM electrolysis. In the case of the alkaline electrolysis, hydroxyl ions are essentially involved, and you have a porous separator. In the case of PEM electrolysis, you have a perfluorosulfonic membrane like Nafion, and you can achieve extremely high current densities, but also good hydrogen purity and of course increase the level of safety. Just to focus on the PEM electrolysis, that seems to be one of the most important technologies for the next future. This is the core of the system. This is a membrane electrode assembly that was dismantled after several thousand hours operation in our laboratory. You can see the catalysts are coated on the membrane. This is the catalyst coated membrane approach, and you can really achieve extremely high current density in the order of several ampere square centimeter, slightly above the thermoneutral potential at cell voltages about 1.8 volts, etc. Another important aspect that this technology can produce extremely pure hydrogen. And of course, the approaches to understand the performance of these systems is to carry polarization curves at different operating temperatures using different catalyst loadings and analyze by C impedance spectroscopy, which are the rate determining step in these devices. Of course, these devices use precious metal electrocatalysts and perfluorosulfonic membranes, but also titanium bipolar plates. All these materials are critical raw materials, included in the critical raw materials list of 2020. And this is one of the main drawbacks. Otherwise, this technology has great advantages, especially combining with wind power and the solar power can really address the intermittent power production with warm startup, with warm response in less than 1 second, and no relevant degradation after several start and stop cycles. And this is something that we have carried out in the project HPEM2Gas that I had the honor to coordinate. And in this case, we have addressed operating at high current density. Why high current density? Because, and of course, high efficiency, because current density is inversely related to the capital costs. So this is one approach to decrease the cost of the technology, of course, but also we need to still keep high operating efficiency because, of course, at the moment the cost of renewable electricity is not so cheap. So this is another important aspect. You know, this technology is based on a PEM electrolysis stack, in this case a stack of something like 70 cells, providing operating at 200 kilowatts, and this is let's say an innovative technology developed by ITM Power based on a hydraulic compression, allowing to achieve extremely high efficiency at high current density. And this is a picture from the regarding the field testing activities that we have carried out in this project in the northwest of Germany, where you can see the stack allocated into the system and the system connected to the gas uptake station. The hydrogen produced from the surplus of renewable energy is fed into a local natural gas grid. Another technology that is has good perspectives, since I already mentioned that PEM is based on critical raw materials, and liquid alkaline electrolysis is operating at low current densities compared to the PEM. So the new technology is the anion exchange membrane, electrolysis technology that is using an anion exchange membrane. So we are still dealing with an alkaline environment, so we can get rid of critical raw materials and we can use cheap and abundant materials and still operating at high efficiency and high current density. However, at the moment, the gap between AM and PEM is about 300 millivolts. 300 millivolts is corresponding to something like 10% energy loss at 2 ampere square centimeter, essentially due to the polarization resistance. So regarding AM technologies, technology, there is still a long way to go in order to achieve comparable performance to PEM. And okay, I think I can now move to Robert for completing this lecture. Robert, can you? The floor is yours, please.
Yeah.
Go ahead.
Thank you, Antonino. I will continue. Yeah, well, we've heard about photo-electrochemical conversion, producing hydrogen, and just now on electrolysis. what these types of technologies for hydrogen means is that the hydrogen produced will still contain some water and also traces of oxygen. So to attain high purity hydrogen, you need to remove those oxygen and water from the hydrogen stream. Generally, oxygen can be removed catalytically in a so-called deoxidizer reactor. It's a reactor filled with catalyst material, and the oxygen, the few ppms of oxygen in the gas stream reacts on a catalyst surface with the hydrogen and producing some heat, but also some water. And this water, with the water which is already inside the gas stream, can then be removed using a temperature swing adsorption system. That's the basics of TSA, temperature swing adsorption, is that you have a preferential adsorption of water on a sorbent material at low temperature, and in the next phase you desorb your water at a high temperature using a dry gas flowing through your reactor. So in essence, wet hydrogen is being fed to a vessel filled with this sorbent material, and the dry hydrogen exits out the top, exits the vessel. In fact, that would be a kind of a batch process, but if you want to have a continuous operation, you can have 2 or more vessel systems. So that means that one of a vessel is absorbing the water and producing pure dry hydrogen, and the second vessel is then in one of the other process steps in this TSA swing adsorption process. That's either under depressurization or desorption with at a high temperature with the dry gas feed, or in a cool down situation whenever all the water has been desorbed from adsorbent material, or finally in a standby mode.
Robert, may I ask you to please summarize?
I'm almost ready. On the right, you see a small picture of 2 TSA vessels for the photo H2 system. The photo H2 system consists of one panel producing quite a small amount of hydrogen, too small for commercial compressors. So the flow is first collected in a buffer vessel, and then intermittently this buffer vessel is emptied using the compressor, and then this gas feed is sent through the deoxo reactor and the TSA. And on the right, you see the complete system, the hydrogen purification system for the H2 system. Okay. Thank you. And now we are open for questions.
Okay. Thank you to all the presenters for giving the big picture on solar hydrogen production. So it has been very interesting to have this comparative overview of what technology options are available.